Ladies and gentlemen, good morning. I am BoFeng Bai from State Key Laboratory of Multiphase Flow in Power Engineering, Xi'an University, China. I am honored to have the opportunity to speak at this meeting. I would like to present my updated research work, two-mode Eddy-Viscosity model for compressible supercritical fluid turbulence. My talk mainly consists of 4 parts. In the first part of the report, I'm going to begin with the research background and the issues of supercritical fluid. The special thermophysical property lead to very high compressibility, affecting turbulence properties. Therefore, I will introduce the turbulent heat transfer fundamentals, including statistic properties and structural properties in the second part. Another interesting topic is how to model this peculiarly compressible turbulent. So, in the third session, I will talk about the turbulent modeling theory. The last part is the summary. As we know that the turbulent heat transfer of supercritical fluid widely exists in the process of energy conversion and utilization. The table lists the several common supercritical working fluids in the industry, such as supercritical water used in the clean coal-fired power generation, the coal gasification for hydrogen production, and the 5th generation reactor. Supercritical CO2 is used as working fluid in Brayton cycle for power due to its high density, low viscosity, and lower critical temperature. And it has wide applications in material fabrication, chemical engineering process, and et al. Supercritical helium, nitrogen, and hydrocarbons are used as coolant for jet engine, regenerative cooling in rocket motors, coolant or fuel for jet engine, respectively. A supercritical fluid is any substance at both temperature and pressure above its critical point. Distinct liquid and gas phases do not exist. Left figure gives the phase diagram of CO2. The equilibrium line of gas and liquids has an endpoint at a certain pressure and temperature. This is so-called critical point, and the region above the critical temperature and pressure is named supercritical region. The right two figures give the thermophysical properties of supercritical water and carbon dioxide at certain pressure above its critical value. As shown here, there is a peak value of specific heat, and the density, thermal conductivity, and viscosity decrease drastically. This region is called pseudo-critical region. We could see that the CO2 has higher density and lower viscosity than water, which means that CO2 is a good working fluid in the thermodynamic cycle. The thermophysical properties of supercritical fluid are much different with ideal gas. The table gives the density, thermal expansion rate, and the isothermal compressibility of water, CO2, and air. The density and thermal expansion rate of supercritical water and supercritical CO2 are about 100 higher than air, while their isothermal compressibility is much less. In order to further review the cause of special turbulent properties, the density fluctuation is analyzed. Here, the variation of density is expressed as a function of the temperature variation and the pressure variation. And by integrating this equation from instantaneous density to average density, the differential form of the density fluctuation is presented in this equation. We can see that the density fluctuation is related to both exothermal expansion rate and isothermal compressibility. Because of the former is much greater than the latter, the effect of pressure fluctuation on density fluctuation is small. As mentioned earlier, the thermal expansion rate and density in the pseudo-critical region are much higher than the ideal gas. Thus, a small fluctuating temperature would cause a significant density fluctuation. This figure shows the density fluctuation of supercritical water in the channel flow. The results are obtained by our DNS calculation on a supercritical channel flow. We could see that the root mean square of the density fluctuation is not negligible compared with the mean density. Due to the strong density fluctuations, supercritical fluid turbulence has many special features comparing with the traditional compressible turbulence theory for high-speed flow. As shown in Figure A, the Van der Waals scaling law fails to describe the mean velocity profile of supercritical fluids. Figure B shows that the energy spectral in the pseudo-critical region appears a -1 power law in the initial subrange. This is different from the incompressible turbulent spectral with -5/3 power law. As shown in Figure C, the quadrant analysis describing the coherent motion are also given here. Two conditions, no density fluctuation and strong density fluctuation, are compared. We could see that the coherent motion are stressed in the strong density fluctuation cases, especially for the cold sweep and hot ejection in the heated boundary layer. In Figure D, it is also found that the ejection of high-density fluid stresses the energy transport, changes the distributions of temperature and density, meaning that the turbulent production will be improved, leading to the probability density function of the fluctuating temperature deviates from the Gaussian profile, as observed from the Figure E, which do not satisfy the traditional statistical theory. We summary here why the traditional modeling theory of compressible turbulent for high-speed flow are not suitable for supercritical fluid, leading to the large errors. First, density fluctuations plays a significant role in the turbulent transport. The biggest terms related with the fluctuation described in the followed equations cannot be neglected. In addition, the left figure shows the related Reynolds stress of supercritical Helium pipe flow. It is obvious that the terms related to Reynolds stress have big value. Thus, Markovan's hypothesis of negligible density fluctuation related with Reynolds stress will invalidate for supercritical fluid. Second, a very peculiar M-shaped velocity profile will form in supercritical fluid flow, leading to failure of linear Reynolds stress constitutive equation. The third, comparing with the pressure fluctuation related diffusion term in TKE equation, it's clear in the right figure that the effect of pressure fluctuation on turbulence is significant and cannot be ignored in the modeling. Here is our investigation roadmap. To review the supercritical fluid turbulence mechanics and modeling theory, we focus on the compressible effect on turbulence, which is a special kind of compressible turbulence. The investigation includes statistics and scoring, energy budget, turbulence structure, and turbulence modeling. In the second chapter, we will discuss the turbulent heat transfer characteristics of supercritical fluid. We first establish the direct numerical simulation method. Then we will investigate the turbulent statistical properties and structural properties. We first introduce the DNS methodology. The calculation case is a supercritical water channel flow. The upper plate temperature is above the pseudo-critical temperature, while the bottom plate temperature is below. We conducted this simulation based on projection method under low Mach number condition. Compared with the incompressible flow, there is an additional term in the pressure portion equation, which is related to the varying density with time. Additional streamwise body force is applied in order to guarantee the streamwise mass flow rate balance. Here, we also give the calculation parameters and the grid number. Now, we discuss the scaling law. From figure A, we could observe that velocity profiles of supercritical fluid turbulence could not collapse with the Van der Waals scaling law. We know the Van der Waals transformation relies on two conditions. First, the missing length linearly varies versus y, and the common coefficient is a constant. Second, total shear stress conservation in the boundary layer. But we found the common constant decreases with increasing compressibility, as shown in figure B. Therefore, the Van der Waals transformation falls in supercritical fluid flow due to the failure of Prandtl's missing length theory. Due to the failure of the Prandtl missing length, we try to establish the velocity scaling law. Based on the damping function and asymptotic analysis of velocity fluctuation, the Markowitz scaling formula is developed, and the new velocity scaling law for supercritical fluid is obtained. The result agrees well with DNS as shown in this figure. Now, we talk about turbulent transport bucket terms. Here, we give the compressible turbulent kinetic energy equation. The physical interpretations of the bucket terms include: first, production due to the interaction between the turbulent shear stress and strain rate. Second, diffusion due to the velocity fluctuation and pressure fluctuation. The third, viscous diffusion due to the viscous stress. The fourth, pressure dilatation reflecting the interaction between the pressure fluctuation and fluctuating velocity divergences. The fifth, additional mass flux transport caused by the pressure gradient and the viscous stress. The sixth, dissipation due to the work of viscous stress. The figure gives the turbulent bucket in channel turbulent. The main contribution to TKE came from production term, diffusion term, and the dissipation term. the effect of pressure dilatation is still small, and it still has redistributive property. This is useful to develop turbulence model. Now, we will introduce the compressible effect on energy cascade. Helmholtz's decomposition law was used to decompose the turbulence into sonodal mode and compressible mode. We found that the influence of compressible mode on both the large and the small scale motion are significant. The left figure extracts the scaled turbulent kinetic energy in the pseudo-critical region. The peak value of the ratio of Kc and K reach 20%. Let's to say the contribution from the compressible mode is significant. Identical consideration holds for turbulent dissipation rate, as shown in the right figure. These properties are quite different from the high-speed compressible turbulence. For example, compressibility is only a fact in the subgrid scale. Another observation is about the effect of compressibility on the local equilibrium. We found that local equilibrium still exists in the pseudo-critical region. The figure illustrates the anisotropic part of Reynolds stress versus Y plus in different Rayleigh number cases. Clearly, the Reynolds stress anisotropy basically kept unchanged, as seen in the figure. Based on DNS data on an isotropic part of Reynolds stress and the following derivation, the conclusion that the turbulence production equal to dissipation can be drawn. This indicates that the local equilibrium exists in supercritical fluid turbulence, even with high compressibility. And for turbulent structure, it is found that the fluctuating velocity near the wall appears as a strict structure, while they gradually become unstable and break up to Baudi's structure as the wall normal plus Y plus increases. In the last session, we have discussed the peculiar properties of supercritical flow turbulence. Now, we will focus on turbulent Eddy-Viscosity modeling theory. Based on the physical mechanics of supercritical fluid turbulence, we first established the statistical equation, and then we obtained the modeling of physical parameters, including turbulent kinetic energy, turbulent dissipation rate, and eddy viscosity. Finally, the modified model is obtained. Our strategy to develop the two-mode eddy viscosity model for compressible supercritical fluid turbulence is as follows. Helmholtz's decomposition is employed to divide velocity into two modes, including the compressible mode needed to be moded. Based on the turbulent spectral theory, we establish the mathematical description of the spectral equation, which is a neutral for compressible turbulence modeling. Then we solve the transport equations of the energy spectrum, and each solved parameters is modeled and correlated with the eddy viscosity. The advancements of this strategy include Helmholtz's decomposition is a universal law, independent on compressibility, turbulence scale, and flow properties at all. And The transport equations, turbulent parameters of the compressible part, could be derived and incorporated into the Eddy-Viscosity formula to represent the effect of fluctuating density. By Helmholtz decomposition theory, the velocity vector is divided into the solenoidal part and the compressible part. The solenoidal part is free of divergence and represents the shearing motion of the fluid. Its properties are same as the incompressible turbulence. The compressible mode is a rotational and represented the expansion or compression of the fluid. In order to clearly show the relationship between the solenoidal mode and the compressive mode, we transform them into the Fourier space as is shown in the figure. The velocity vector of compressible turbulence could be divided into two components. One component is parallel to the wave number vector, and the other component is perpendicular to the wave number vector. Thus, in mathematics, we obtained two projects in Fourier space, P and pi, to describe the relationship between the solenoidal mode and the compressible mode. In order to obtain the spectral equations of compressible mode, we transform the non-conservative form of the Navier-Stokes equation into the Fourier space. The velocity spectral is obtained as equation 1. With the above two projectors, we get the velocity spectral equation of the compressible mode based on the incompressible moment equation. The column first-order statistic gives the velocity spectral equation of the solenoidal mode and the compressible mode. These equations consist of unsteady term, viscosity, viscous term, the convective term, and additional fluctuating pressure-related term. We would further obtain the transport equation of the second-order moment based on the velocity spectrum equation for fluctuating UC. We could find there occurs a new unclosed term, the third-order moment. In a similar way, to obtain the transport equation of the third-order moment, the unclosed fourth-order moment occurs in the transport equation, as shown in equation 2. Since the degree of internal compressibility is quite different in different temperature range at the supercritical pressure, the compressibility is strong in the pseudocritical range, but is weak when the flow temperature is far away from the pseudocritical range. In order to guarantee the universality of the turbulent model, we will discuss the above two conditions respectively. If the flow temperature is away from the pseudocritical region, the energy spectra of the compressible mode is much lower than that of solenoidal mode. According to this, we will simplify the transport equation of the third-order moment. Also, note that the contribution of pressure fluctuation is limited since the pressure fluctuation-related moments are negligible when Mach number is below. First, we will analyze the spectral equation of the compressible mode in the non-pseudocritical region which means a weak compressive condition. In order to close the fourth order moment, here we introduce the quasi-normal hypothesis in the statistical mathematics. The fourth order moment could be expressed as the convolution of second order moment. In fact, this hypothesis is acceptable if the probability density function of fluctuating velocity is similar with Gaussian profile. Here, we show the PDF of supercritical fluid turbulence at different vol normal position in pipe flow. The DNS data come from the reference work on the supercritical CO2 flow with the inlet Reynolds number of 360. The velocity fluctuation PDF matches with the Gaussian distribution well. Thus, quasi-normal hypothesis is employed to close the moments composed by the velocity fluctuation. The transport equation of the second order moment is simplified as equation 1. So far, we have obtained the mathematical description of the compressible mode. By solving the transport equation of third order moments and introducing the third order moment into the transport equation of second order spectral tensors, the second order spectrum tensor will be closed. Furthermore, according to the relationship between the second order spectral tensor and the energy spectrum, the closed energy spectrum is obtained, as shown in the equation 1. The seat in the equation represented the characteristic timescale of the third order moment. The function of f included the two projectors in the Fourier space and the wave number representing the interaction among the wave number k, p, and q. The x, y, and z represented the three constant values of the triangular formed by wave number k, p, and q, as is shown in the formula 2. And the integral area is expressed in this figure. If the flow temperature is in the pseudo-critical region, the energy spectrum of the compressible mode is much significant than that of sonodal mode. They are in same order of magnitude. Using the similar way, we could obtain the energy spectral equation in the pseudo-critical region. The form of the energy equation 1 is quite different from that away from the pseudo-critical region. The function a to f have the physical meanings of the effect of shear motion on compressible energy spectral, interactions between the shear motion and the compressibility, and effect of compressibility. The mathematical description for each function has been illustrated in the bottom of this page. The integral area is same as that the non-pseudo-critical condition. We see that in the pseudo-critical region, the compressible energy spectrum is driven by the turbulent energy exchanged between the two modes, including not only the transport within the sonodal mode or the compressible mode, but also the interaction between the two modes. Now, we will seek the energy spectral solution of compressible mode. Firstly, we will discuss the non-pseudo-critical region. Under statistically on a steady condition, the characteristic time scale set could be simplified. then the energy spectral equation could be reorganized as equation 1. We introduce Frisch-Volk as the energy spectral of sonodal mode in equation 1. The result shows that the transport terms in the energy spectral equation shows a -1 power law versus wave number k as shown in the upper figure. Thus, we could finally get the solution of energy spectral away from the pseudo-critical region, as is shown in the equation 2. The energy spectral equation shows a -3 power law versus wave number k. Now, let's solve the energy spectral equation in the pseudo-critical region. The equation is solved by the composite simplicium rule for numerical integral and fourth-order Roncoulomb method for time advance. The final result for the energy spectral is given in the figure. The -1 power law of energy spectral could be observed, and this power law is different from that of conventional compressible turbulence or the incompressible turbulence. This result agrees with the dimensional analysis as well as DNS investigation conducted by the reference work. Now, we have obtained the -1 power law of the energy spectral. Setting the formula as the energy transfer flux and utilizing the energy cascade formula, which means the turbulence energy transfer rate is equivalent to the turbulent dissipation rate. The dimensional analysis yield the equation 1. Thus, the expression of energy spectrum in the pseudo-critical region is equation 2. Based on the solution of the energy spectrum, the turbulent viscosity formula, considering the compressible mode, is proposed. We transform the information of the Fourier space back into the physics space, and we will get the solution of the turbulent kinetic energy, turbulent dissipation rate, which determines the value of the Eddy-Viscosity coefficient. The solution of the viscosity have been given here for the region away from the pseudo-critical region and the pseudo-critical region, respectively. Please note that the lower limit and the upper limit of the integral are taken as the wave numbers corresponding to the integral scale of turbulence and the Kolmogorov scale. The constant in the Eddy-Viscosity formula are obtained by DNS channel flow data and the numerical test. Combined with the standard K-epsilon model and the modified Eddy-Viscosity formula, we calculate some supercritical flow cases. The predictions on heat transfer coefficient of supercritical water pipe flow have been given here. We could see that after the modification, the deficiency of the transitional mode in the pseudo-critical region is effectively eliminated. The prediction error are lower than 10%. And the prediction of mean velocity of supercritical CO2 pipe flow have been given here. Our developed model could give in good agreement with DNS data over the entire cross sections. This result shows the Reynolds shear stress prediction of supercritical CO2 pipe flow. Traditional models underestimate the Reynolds stress in the pseudo-critical region, since the additional turbulent stress caused by the compressible mode is not modeled correctly. But the prediction of our developed model could correlate well with the DNS data. This result shows the turbulent heat transfer and turbulent production of supercritical CO2 pipe flow. The turbulent production gradually decreases along the flow, and this is due to the flow acceleration related with thermal expansion. A better agreement between the results of our developed model and DNS data can be observed here. We show the predictions on the mean temperature profile and the wall normal position of the pseudo-critical point in the channel flow. The case used supercritical run 134A as working fluid. The bottom and the top walls are kept below and above the pseudo-critical temperature respectively. It can be seen that the result of temperature profile given by our developed model matches DNS data well. Another critical parameter, pseudo-critical temperature position, predicted by different turbulence models, have been listed in the table. Our developed model can give the close-set result compared with the DNS data, while the traditional turbulent model have great error in the predictions. Here we show the predictions on mean velocity and the Reynolds stress profile in channel flow. A better agreement between the results of our developed model and the DNS result are also achieved. The final part is the summary. In this lecture, the fundamental and modeling of supercritical fluids turbulence are reported. The conclusions are summarized as below. First, Markovit's hypothesis is invalidated due to density fluctuation. This leads to the invalidation of Van der Drast velocity scaling law and Pront's mixing length theory. A new velocity scaling law is proposed based on the modified Markovit scaling for Reynolds stress. Second, compressibility profoundly influences on the production and the diffusion of turbulent kinetic energy, but a local equilibrium still exists in supercritical fluid turbulence. Third, the two-mode Eddy-Viscosity turbulence model for supercritical fluid turbulence is proposed with good prediction. That's all. Thank you for attention. Any questions and discussions?